Continuing on the bearing capacity of shallow foundation. So now we are moving to estimating of bearing capacity with SPT, so standard penetration test. For example, this is a test that we done during site investigation, subsurface exploration, so underground before we go for a certain building. In the initial ground investigations, some cases we might do the standard penetration test. So let's say in the standard penetration test, I think we will learn that separately, but we will be getting N60 value. That's the field standard penetration number. So with that number and with the dimensions of the foundation, for example, the foundation can be the, let's say if it's 2 meters, so that width would be more than 1.2. If the width is like 1 meter, it comes under this category. Either way, based on the width, we can use either this first equation or the second equation to figure out the allowable or net bearing capacity. Okay. So it's a net bearing capacity. So the equation consists of, you can see in 60 values, width of the foundation, elastic settlement of the foundation expected. So that is a design factor. So this is something I like to mention again. So some cases we can consider this like 25 millimeters or something like that. But some cases client, if it's a sensitive project, if the client is so specific, so client may request, okay, design for 15 millimeter elastic settlement like that. So lowering the elastic settlement, then we need to expect high bearing capacity solve. And then FD is the depth factor based on the depth. Okay, so depth of the foundation compared to the width of the foundation. So we use this equation as a quick estimate when we're doing the standard penetration test. So getting the number of counts, blows, then we can figure out if we have a like a 2 meter foundation, like with 2 meter, 1.5, 1.5 like that. It doesn't need to be square, like any shape. We can figure out the allowable or ultimate bearing capacity or net bearing capacity. Right. Let me clear this up. Right. So moving on, there's another site test, in situ test we can do to figure out the bearing capacity. We call that plate load test. So what it does, so a pit, like a hole on the place of the interested location is cavity. So this is the pit. Okay. So the condition is the width of the test pit should be at least 4 times the width of the bearing plate. So it means this is the bearing plate. If this is B, this width should be minimum 4 times the width of the plate. Okay. And then so with a hydraulic jack, we can apply load like a vehicle jack or etc. So we can apply a load. So as we apply the load, then we will be checking the settlement or the displacement. So once we apply the load, so we will check what is the another color displacement settlement. So based on the stress or load per unit area, so each load we will be getting the settlement and we are plotting the graph. So load per unit area is actually the pressure. So this is another way to get an idea, get information of the bearing capacity of the soil. So actually most of the ground investigation or site investigation tests. So our idea is to get an understanding of the soil bearing capacity because that's where we're going to build our foundation. So calculation. So as per the graph, you can see we can get with this graph for each load or actually for each stress settlement is calculated. Now the question is the width of this plate is not the width of the foundation. So foundation width may be different. So how we calibrate or how we uh, extrapolate or interpolate what will be the settlement if we have a 2 meter wide foundation, if we have a 6 meter wide foundation. That's where we will be using these two. So when using these two equations, the first one, the ultimate bearing capacity, Q ultimate, can be used find with these two. Difference is for clays, there's a separate equation, and for sandy soils, there's a separate equation. For sandy soils, you can see the plate bearing capacity. Then we have to multiply by a ratio of width of the footing by width of the plate. Okay. So I think it's a bit obvious for a particular given settlement, what will be the allowable bearing capacity or ultimate bearing capacity. Then based on the safety factor, we can find the allowable bearing capacity. Now, if you remember, I told you in some cases, the client insists, okay, I don't need 25 millimeter settlement. I need 15 millimeter settlement, 10 millimeter settlement. So then what we have to find? If we know the settlement of the plate, and we need to find, if we are restricted on the settlement of the footing, so let's say 15 millimeters. So this is from the graph, and width of the plate is known. This will be the unknown. So if you want to limit the settlement, we will have to increase the width of the foundation. Increasing the width of the foundation means what? We are building a larger foundation. Larger foundation means cost will be high. So we can see the difference. So actually a design means what? We need to have a safe design for a reasonable cost. Otherwise, even if you're building a house, you can have a very big foundation, so that will never fail. On the other hand, the project will not be successful if the cost is too much. So in settlement calculation also for clay and sandy soil, two different equations are used. So a given soil, how do you know whether it's a clay soil or sandy soil? For clay soil, you know the C value, cohesion. For sandy soil, most of the time cohesion is zero. There's a friction angle. Okay. Right. So there's a example given. So to use this equation, So ultimate bearing capacity of a 700 millimeter diameter plate as determined from field load test is 280 kPa. Estimated ultimate bearing capacity of circular footing with diameter 1.5. Soil is sandy. So if the question is given soil as sandy or given shear strength parameters, then we can straight away. So sandy soil means we have to use this. So the plate diameter is given, footing diameter or the foundation diameter is given. Ultimate bearing capacity of this is given from plate load test. So you just have to put it into the equation and you will get the bearing capacity high 680 because the diameter is increased. There's another example. So there, the earlier you can see ultimate bearing capacity was given 280. Now you have to read this through the given diagram. So this sort of a diagram is a result of the field test. So let me use red color. Okay. So sandy soil. So the plate size is given. It seems like a square plate. Size of the square column foundation that should carry a load of 2,500 kilonewton with a maximum settlement of 25 millimeters. So now you see, so we have to satisfy two. So in this case, since the settlement is also a parameter, we will have to use this equation. So in this equation, what we are going to do, we're going to assume the width of the foundation. Assume the width of the foundation. Based on that width, we will find the load per unit area. So with that, this load, so this load, 2,500 kilonewton, applied on a width initially assumed as 4 meters. So 4 by 4 meter square foundation. So this load divided by 16 square meters. This is the bearing capacity. So then with the bearing capacity for the load, 156. So 100, this 100. So somewhere here, this value is read as 4 millimeter settlement. So now you're using settlement of the plate is 4 millimeter. So the dimension of the footing is, we assume 4, 2 times 4, and without the footing 4, width of the plate. Width of the plate 0.305. So with this equation or square, we should be getting the settlement of the footing this much. So, but this says maximum settlement of 25 millimeters. So now, if we get a width of 4 meter diameter, 4 meter square foundation, our settlement is less. So since we can go up to 25, we can increase the width. Sorry, decrease the width. So decrease in the width means pressure will be high. Why? 4 by 4 means 16 square meters. The cost will be high. I'll move on to the next slide. So now we can see gradually in the next case, foundation width of 3 meter considered. So imagine if it's 4 meters, foundation area is 16 square meters. But if it's 9 square meters, so almost the area nearly half. So that way, the pressure will be high. But we are interested in the settlement. So this one, settlement is higher than expected. So our answer should be in between somewhere. So you can see answer, if we take like 3.2, settlement comes around 22. So we accept it. So we can say we can have a column footing with 2.2 by 2.2 meters. So this sort of a method we call trial and error method. So we start with a value, we do the calculation and see whether the settlement is higher than the expected or much lower than the expected. So if it's much lower, we need to increase the width a little bit. But when it's close to that, so 22.67, we can even do like, we can even check to 3.3. But since we are later on applying another safety factor, we just say, okay, 3.2 is enough. So try to do those. And now I'm going to talk about the bearing capacity failure. Because all these equations that we saw have been developed assuming the failure will be a general shear failure. General shear failure, the failure mode looks like this. I think with the plate load test, so if I go back, so this sort of a curve, we can see load per unit area, pressure, term times settlement. This, so pressure times settlement. So an actual foundation, this curve, you can see we are in the plate load test, we are only considering up to somewhere here. But if you keep loading, there will be a point it's reaching a maximum and then failing. So that's general shear failure. And then there's local shear failure, in which in local shear failure, you can see there's no sharp high like that, but it gradually increases and then reaches the height or the highest point and then breaks. That's the failure. So punching shear failure, it's a quick one. Punching means it's happening in a very short area. I'll discuss this in a while. And you can see applied pressure. Pressure applicable is much, much less. So you can get an idea from this Q ultimate value. So let's look at one by one. General shear failure. So most of the bearing capacity equations are developed based on assuming general shear failure occurs. General shear failure occurs on foundations we establish on dense sand or stiff clay. So dense sand means, so before we can do the construction, we densify the soil if it's not dense enough, like compaction like that. So in the dense sand, this will be the mechanism of shear failure. Okay. So you can see when we keep applying the load, so our foundation settles downward. And with that downward movement, they are like this area compresses and this area subjected to tension. So the 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 thing you have to understand is this type of a failure, a peak value is clearly defined. I think you can compare with this with shear strength or direct shear test result. So where you remember displacement versus shear stress. So it's a bit similar to this. Okay. Then if you look at the local shear failure, in local shear failure, there's now like a peak like that. Peak can decrease. Only thing is there'll be a change of the sudden change, like a brittle failure of the slope. So you can see in a local shear failure, there are several ultimate Q values. So initially, it reaches a settlement like a first failure load here, and then finally, uh, there's another failure load happening here. Okay, so that's Q ultimate. So that's the ultimate failure. So we say this will be the ultimate settlement. So in any case, if we're deciding for local shear failure, we consider this settlement. Where the local shear failure happen in medium dense sand. So if you don't compact the soil well, there's a possibility to local shear failure or clay soil with of medium consistent. So this is another reason why we need to investigate the ground conditions and if needed to improve the conditions, compaction like that. Then the punching shear failure. So the punching shear failure happens on loose sand or soft clay soil. So loose sand means, let's say you go to a site without doing any site improvements or etc. You just start placing your concrete. Then punching shear failure may happen. So there's no like two failure loads like that. There's just one failure load which is much lower, and this like this we can observe this before the shear failure. The load per unit area gradually increases, but after that, there's sudden settlement increase. So you can see for a small change of load or pressure load per unit area, that's a big jump of the settlement. So settlement is getting large. So that's why we call punching. So it goes like a punch. So I'll show you some videos, if possible, I'll share to describe each of these scenarios. So in general, uh, this is a very good diagram to show what we can expect when we go to work. So you can see along this axis relative density. So then you have to now go back to your lecture notes last semester. What is relative density? And then on the y-axis, that's a factor Depth of the foundation divided by what? R. What is R? It's a ratio, area of the foundation, perimeter of the foundation. So R value is this. Okay. So like depth of the foundation divided by R means divided by B L 2 times B plus L. So, dF divided by R means BL. So BL 2 times B plus L. So now we can see this axis, this parameter depends on the depth of the foundation, width of the foundation, length of the foundation. So foundation dimension. So you can see general shear failure happens most of the time where the relative density more than like 70%, 75%. Other cases, local shear failure. And if you don't compact well, it means loose conditions, then punching showing shear failure can happen. So it's possible think of, like let's say, uh, a simple exercise is, let's say you consider a foundation like the previous example, let's consider 3.2, 3.2, the dimensions that we got. So let's say the depth, I don't know whether they are so depth, let's say 1 meter. So then you put that into this parameter and calculate what df divided by r. So based on that value, and you can see like at least to have this in the general shear region, you need to have at least this much of relative density. So that shows you how much you should compact your soil. So also, there are in some cases, based on the experience, people have assumed some bearing values. So this is given in British standard, presumed, or it means pre-assumed. Initially assumed the bearing capacity values for the description of the soil type, like dense gravel, dense sand, loose sand like that. Okay, so there are condition is width of the foundation not less than 1 meter. So width of the foundation more than 1 meter. Water table at least width times below the base of the foundation. So water table is considerably at a below like a depth. Okay. So this thing also we can use. So this will this bearing capacity table it will give you some idea what is the bearing capacity values of the soil. So those who go on training on site investigation firms, you will see. So based later on, after some time, you can like uh, assume or you can predict, estimate what is the bearing capacity of that particular soil. So soil strength, I think drainage is also another important factor. Drainage means whether the water will drain out. So draining out of water, how it will affect to the foundation, the settlement. When the water escapes, the foundation will settle. Okay. So undrained means there's no volume change, but foundation can deform. Foundation can settle because of the applied load. Then if it's drained, it means water escapes with the foundation construction and therefore foundation settlement happens. So soil shear strength. I think we have discussed this shear strength, but I want to discuss effective stress failure criteria and total stress failure. So effective stress failure criteria applicable in drain condition. It means the water can escape without creating additional pore water pressure or excess pore water pressure while inducing settling. But undrained conditions are what? In a site like, for example, clay soil site, where the soil is less permeable or the process is quicker, so that there's no time for water to escape. Okay. So undrained parameters used for clayey soils and drained parameters is used for sandy soil. So, so that's the summary. And I want to show you a few examples of bearing capacity equations and how we done that. So, because before deriving the ultimate bearing capacity, so we use some of the Tersagi's bearing capacity equations. For example, Tersagi defined for a square foundation, this is the bearing capacity equation. So this N, C, NQ, N gamma, all are factors based on the friction angle. Okay. So for a square foundation, so in the description it says 1.2 meter square footing. For a square foundation, we have to calculate the gross allowable load. So there's another difference. I'm asking allowable load. So if I ask the allowable pressure, that's load per divided into area. So allowable load means what? Stress or pressure multiplied by area. Okay. So try this example. So the parameters are given, and also there you can take other parameters from this table. So initially the Tersagi defined these bearing capacity equations for different type of footing, continuous or strip footing, square footing or circular. But the thing we learned earlier, that's a modified ultimate bearing capacity equation for any shape. That's the easiest one. But why I would consider this, so some cases, if it's a square one, I think you can easily calculate with this. Okay. So you don't need to calculate NC, NQ, N gamma. You can just take those from the book. Like this. So I have shown how the question is done. And next topic, I'm going to talk about the water table. But for the moment, try to do this example on your own. And then after that, we can discuss.